Okay, in this one, we're going to talk about an eigenvalue problem that lies at the heart, the core of a very important technology that we're going to learn about called Fourier series. Okay. Okay, so here is the eigenvalue problem. Same differential equation, but now boundary conditions are different. It's going to be x of negative pi will be equal to x of positive pi. Okay, and x prime of negative pi will be equal to x prime of positive pi. So not only is x the same in the same position at negative pi and pi, but also its derivatives are the same at negative pi and pi. That's the way to think about what's happening here. So again, we ask the question, what values of lambda give rise to non-zero solutions to this boundary value problem? Such lambdas are called eigenvalues. And non-zero functions, so non-zero solutions are called eigenfunctions. Okay. So we again break down by lambda the sign, the SIGN of it. Now, you can go through the calculation for lambda being negative. It's not that interesting, so I'm not going to do it. It doesn't give rise to anything, so I'm just going to say no eigenvalues here. So this does require justification, but I'm not going to provide it, okay, because it's just in the interest of time. Lambda equal to 0 now. Let's think about that next. So if lambda is equal to 0, then again, the general solution, this doesn't change. It's just as before. The general solution is x of t equals at plus b. Now, what do the boundary conditions say about this state of affairs? Well, if x of negative pi is equal to x of pi, then this says that negative a pi plus b is equal to a pi plus b. Okay? So now subtract b from both sides, add a pi to both sides, divide by 2 pi, and we learn that a must be 0. Okay? That's good. Now, what does the second one say? Well, x prime of negative pi is equal to x prime of pi. So what does that imply? Well, x prime of negative pi is x prime of t, notice, is just a. So this is this is automatically satisfied by the by the equation x of t equals at plus b. All right, it's automatically satisfied. In other words, notice the only constraint here is on a. A must be 0. B can be whatever it wants to be. So what I'm saying here is that lambda equal to 0 is an eigenfunction. Or eigenvalue, sorry. And the associated eigenfunction the eigenfunction, well, we can take b to be anything that we want as long as it's not 0. So let's just take it to be 1. The constant function 1. And you can check that if lambda is equal to 0, then x of t equal to 1 is indeed a solution to this boundary value problem. Okay? Great. Excellent. Superb. So we found one eigenvalue, 0. Can we find any others? Well, crucially, yes, we can. So let's see. How about lambda positive? That's the final case that we need to think about. So if lambda is positive, then as usual, as just as before, the general solution in this case is given by x of t equals a cosine lambda, square root of lambda times t, square root of lambda times t, plus b sine square root of lambda times t. Have I turned off my brain? No, this is correct. Good. Okay, now what does this imply about, what do the boundary conditions imply? So let's plug in x of negative pi, the first boundary condition. Let's look at that one. I'm going to do this in colors, okay? So x of negative pi should be equal to x of pi, right? But if I plug in negative pi, I get a cosine of negative square root of lambda times pi plus b sine of square root of lambda times negative pi. Oh, I should put the negative out front. Negative here, pi right there. That's equal to a cosine square root of lambda times pi plus b sine square root of lambda times negative pi, times pi. But the thing that I want you to remember is that cosine is an even function and sine is an odd function. So these negative signs can go away. The evenness of cosine means that it's equal to this. And the oddness of sine means that we put a negative sign out front like this and get b sine square root of lambda times pi. On the other side, we get a cosine square root of lambda times pi plus b sine square root of lambda times pi. Now, notice that the a cosine square root of lambda times pi kill each other. We can just sort of do this move like that, right? And I can add b sine square root of lambda times pi to both sides and divide both sides by 2. And so I learn in the end that 0 is equal to b sine square root of lambda times pi. Okay? So either b is 0 or sine of square root of lambda times pi is 0. This is true if and only if either b is 0 or sine of square root of lambda times pi is equal to 0. Right? One or the other has to be true. Maybe both, but one or the other has to be true. Okay. Now, that's only the first boundary condition. Okay? The second boundary condition, I'm going to leave this as an exercise for you. So if you check what x prime of negative pi being equal to x of pi implies, this is true if and only if, okay, either a is 0 or sine of square root of pi, square root of lambda times pi is 0. Okay? Now, remember, we want non-zero solutions, okay? We want non-zero solutions. So we can't have both b being 0 and a being 0. We can't have it. So we have to have, in order to have a non-zero solution, sine of the square root of lambda times pi being 0. One way or the other, right? So to obtain an eigenfunction because of the non-zero condition, we need that this sine of square root of lambda times pi be 0. But just as in the previous example, this is equivalent to square root of lambda times pi being an integer, right? Integer multiple of pi, which is equivalent to lambda being equal to k squared. For k equals 1, 2, 3, etc. Okay? And in this case, so what we found is that we know the eigenvalues now. the eigenvalues are given by lambda equal to k squared, okay? And the eigenfunction associated with this is, well, let's just think. If lambda is equal to k squared, then these two conditions are automatically satisfied, okay? And in particular, that's going to mean, I don't care what A and B are. They can be whatever they want to be. Because no matter what A and B are, as long as this condition is satisfied, which it is, if lambda is equal to k squared, then I'm going to get a solution to my boundary value problem. Isn't that cool? And so what that means is that for each eigenvalue, we actually get two linearly independent eigenfunctions, a cosine k squared t, or cosine kt, and a sine kt. And we can take an arbitrary superposition of them, okay? So the way I'm going to think about it is that I have an eigenfunction associated to each eigenvalue. You can have, remember when we were doing eigenvectors, sometimes we'd have a matrix that looked like this, lambda, lambda, 0, 0, for example. And we had more than one eigenvector associated with that eigenvalue, lambda, right? Same thing here. We have more than one eigenfunction. In this case, the eigenfunctions are cosine kt and sine kt. And again, here k is an integer. Alrighty? And so we solved the eigenfunction problem here, this second one. And this is one that is very, very important for Fourier series, okay? What is the conclusion? We have lambda equals 0 as an eigenvalue, and the associated eigenfunction is this one. And lambda equal to k squared are eigenvalues, and we have two eigenfunctions associated with each eigenvalue. Okay, cosine kt and sine kt. Okay, the idea here is that we are going to be able to write periodic functions. Okay, we're going to be able to write periodic functions, okay, as sums, infinite sums of these functions, these eigenfunctions that we just found. Okay, in the next video, I want to just discuss some of the properties of solutions to these eigenvalue problems that give rise to the Fourier series machine. See you in the next one.